speaker for the session, Scott Kaplan.
Hi everyone, thanks for coming. Like I said, my name is Scott, and today I'm going to be talking a little bit about natural gas. And I wanted to understand its substitution for oil in the U.S. transportation sector through 2020 and the effect on greenhouse gas emissions. So, quick background. I'm sure all of you have at least heard a little bit about the recent boom in natural gas production in the U.S., a lot of which has to do with fracking. So you can see in this first graph here, this is the EIA, Energy and Information Administration projections of natural gas use through 2040. And you can see here that what fracking does is it increases our ability to extract shale gas. And you see here that the increased projections is pretty astounding. And in the second graph here, we see that the oil reserves in the U.S. are also decreasing and have been decreasing despite this little bump in the last few years. But you can see here that the increase in natural gas is just it's spiking, and it's continuing to do so just with the continuous advances in fracking and movements to new wells. So what's the motivation for my study? So basically, cycles of substitution occur between all different kinds of energy products. You can think of natural gas for coal and electricity, biofuel for oil and the transportation sector. A lot of it's based on availability of different energy sources and relative demand. It's also important to consider natural gas in the context of climate change. It actually emits only about half the emissions of coal, and 60% of those generated by oil. And these are CO2 emissions. So obviously, from the surface, natural gas looks like a pretty clean alternative fuel to use, despite it being a fossil fuel still. However, there is sort of, there's more than meets the eye with natural gas. And you see here that methane leakage from natural gas, and natural gas is essentially, it's methane. And methane is 30 times more potent than CO2 as a greenhouse gas. And along the entire natural gas supply chain, you have different levels of leakage of this methane into the atmosphere. So there's a lot of studies have been done about how much methane is leaked, but really there's no consensus whatsoever. There's a huge range. Studies that say it's close to 0%, and studies that say it's upwards of 10 to even 15% of total natural gas production. And this is just a quick diagram to show you where the methane leakage occurs across the entire supply chain. You can see it starts even from the drilling site all the way through the end use, in the home for heating in this case. And the EPA estimates it at 1.5%, but there's been a lot of controversy over that number, especially in the last year or so. So it's also important to look at sort of what I looked at in my study in the context of policy. And many countries have already introduced pricing schemes for different kinds of emissions. You have NOx pricing schemes, sulfur dioxide pricing schemes, etc. But what I wanted to look at was a carbon pricing scheme. This is sort of a relatively new phenomenon. You have regions like Europe implementing cap and trade, also California with AB 32. That's also cap and trade for carbon emissions from different energy sectors in California. But you also have different other measures like a carbon tax and mandates. So all these carbon policies that are being looked at right now, at least up to very, very recently, are looking at monetizing CO2 emissions, and this is just the final end result emissions you burn out of your car or from the electricity end use in your home. But they don't really price methane emissions, and you can see why this might create an immediate sort of problem for natural gas, in that you have these leakages of natural gas that aren't being priced. So you don't really know if natural gas is as clean as it's made out to be, with these 60% less carbon emissions than oil and half those coal. So that's sort of the motivation for my study going forward. Why did I look at the transportation sector? Two very simple reasons. One, natural gas can be used as a travel fuel. It is used as a travel fuel currently in some extent to public transportation and taxis. But also because the transportation sector is pretty homogeneous in its energy resource makeup, in that it uses mostly oil. Obviously you have biofuel to some extent, but it's easy to sort of kind of tune that part of it out and just look at oil versus natural gas. So what did I ask in my study? I wanted to understand how recent discoveries of shale gas in the U.S. would affect the substitution of natural gas into the transportation sector with and without introducing this hypothetical carbon tax. And specifically, I wanted to understand the effect of the substitution on total potency of greenhouse gas emissions. And I chose 3 different leakage scenarios, 0, 5, and 10%. This is just based on the range I found in the literature. There's even leakages that are seen in the literature up to 15%, like I said. So how did I go about answering these questions? What I essentially did was I went to the EIA database, a very extensive database with lots of different kinds of data, and collected data on 7 independent variables from 1997 through 2011 related to natural gas and oil. And these are basically production variables like consumption, proven reserves, price variables in natural gas and oil, and infrastructure variables like number of fueling stations. And my dependent variable in my study was natural gas used as vehicle fuel. So what I did is I took each of my independent variables and used Excel to extrapolate. So this is the 1997 through 2011 data, and I fit a trend line to it. You can see this is clearly a quadratic trend upwards. Some of the variables had linear trends, and I fit a line, as you can see here, and used that line to extrapolate from 2012 through 2020 and obtain these estimated data points for all my different independent variables. And this is consumption, you can see here. But like I said, I had price and infrastructure and stuff like that. So then I developed a regression model to understand the effect of each of these independent variables on my dependent variable, which is natural gas vehicle fuel consumption. And what I essentially did was I plugged in my extrapolated values that I obtained from 2012 through 2020, and these T's represent that each time period I had a different data point. Plug those into each of their respective sort of variables in this equation. And these beta terms here, all they do is they estimate the marginal effect of each of these different independent variables on my dependent variable. And this allowed me to obtain data from 2012 through 2020 on natural gas used as vehicle fuel. So now, with all this, I have data from 1997 through 2020 on natural gas, on all these different data points, both independent and dependent variables. So that gave me data for a no-carbon policy scenario. This is unmanipulated data, unchanged, just from the EIA and my model. But I also wanted to calculate the scenario under a carbon tax, and what I did was very simple. I took a price elasticity of demand of -0.7 and a carbon tax of $12 per ton of CO2. Both of these are based in the literature I looked at. And this elasticity of demand number is essentially, it's relatively standard for a transportation fuel, inelastic. All that means is that with a 1% increase in price, you have a -0.7% decrease in quantity used for that product. And what I was able to do is simulate the substitution of natural gas. And you can see here that in 1997, with both a carbon policy and no carbon policy, you have a market share of natural gas in the transportation sector only 0.3%, so really not much at all. But when you see over here is even without a carbon policy, just normal market forces promoting natural gas, and this is just increased availability and supply and lower prices, you have a 2.72% market penetration rate of natural gas at this point. And with the carbon policy, you don't really see much of a difference here, although I will show you that there is some significance to this difference. You see 2.76% market share of natural gas with a carbon tax. And that's simply because the carbon tax promotes natural gas use, simply based on the fact that natural gas is cleaner from a CO2 emission standpoint than oil. Like I said before, it's about 60% of the emissions of oil. So this is where sort of my results got interesting. And basically, it's important to know that the transportation sector has seen a 50% reduction in oil over from 1997 through my estimated 2020 period. And this has nothing to do with, this is just reduced transportation demand. So you see here with no carbon policy, you have a 50% reduction in emissions over this time period. But with a carbon tax, you have an estimated 52% reduction in emissions. And this is no leakage involved at all. So this is just simply CO2. You can see at the bottom here that with natural gas, with the carbon tax, you have 2 million tons lower CO2 emissions in 2020 than under no carbon policy. And that's approximately in 2020, you see the transportation sector emitting an overall level of like 100 million tons of CO2. So it's a significant reduction in that case. This is a really interesting result. So this is the same thing as on the last graph. But when you introduce 5% leakage, and what I mean by 5% leakage is 5% of the total production of natural gas used, you have 5% of the total natural gas used is leaked into the atmosphere and not used. So you have obviously you have the same 50% for no carbon policy, but because the carbon tax itself promotes natural gas use from the CO2 emission standpoint, it doesn't account for these leakages, you see that overall emissions reduction is now equal to no carbon policy. And with 10% leakage, it actually is worse off for emissions because you're really supporting natural gas without really looking at this leakage level. So it's really, I mean, this graph says it all. It's really, really important that we understand leakage, at least in a 5% range before we start implementing carbon taxes and other carbon policies to try and promote natural gas without even knowing its leakage levels. So going back really quickly, I mentioned that the substitution rate under a carbon tax versus carbon policy was not that great. 2.76% versus 2.72%. And there's several factors that might explain this. Three main ones that I thought of were limited natural gas infrastructure. In the U.S. in 2011, you only had 910 natural gas fueling stations, where you had almost 160,000 gasoline stations. Very low natural gas prices. So this is important because, I mean, you see here the average natural gas price in gallons of gasoline equivalent is $1.22, compared to $3.10 for a gallon of gasoline. And that's important because, I mean, this is already a huge price incentive to switch to natural gas. I mean, you're paying almost $2 less per gallon of natural gas than you would for oil. And when you implement a carbon tax, it's not going to change this price incentive by very much. It'll increase the gallon of gasoline by 11 cents, like I said before. Natural gas will go up by 60% of that, 6 cents something. That's not going to change someone's decision if it's already this great of a disparity between the prices. And this last point kind of relates to the second point, and that's that natural gas, there's some shadow price for natural gas. And what a shadow price is a price that's not really implicitly valued in this price right here. So you might imagine that the reason why someone might not choose to use a natural gas vehicle is there's not a lot of fuel pumps, it's hard to access. Types of cars you're able to purchase, natural gas vehicle models are extremely limited, and tank storage capacity, natural gas vehicles typically can't hold as much as an oil car. Also, they might be concerned that low natural gas prices may not last. I don't think that's valid. I think that they will, especially in the U.S. So that's not so much of a concern. And really quickly, what are the next steps based on this study? So there's some talk about implementing what's called a carbon fee alternative, and this is exactly what we need. It's a way of pricing different emissions differently based on their relative strengths and harmfulness for the atmosphere. So the only caveat with this is, like I said before, leakages aren't really known to even like a 5% level, 10% range. Without accurate leakage monitoring, there's no way we can implement a type of policy that prices leakages without knowing how much is actually happening. And you can see, even between a 0% leakage and a 10% leakage, there's still that makes a difference between whether a carbon tax is useful or not. So that's a great next step. And we also can include additional variables in the model, other measures of infrastructure like pipelines, number of well sites, expected well sites we drilled, trade restrictions. The U.S. is really looking at exporting natural gas at this point because they have so much and it can generate a lot of revenues for the country, help balance the trade, etc. And different types of policy measures, like I mentioned up here with the carbon fee alternative. It'd be interesting to see under different types of hypothetical policies what would happen to natural gas substitution and the resulting emissions of that. So that's it. I just want to acknowledge basically the same people that everyone else has been acknowledging already, and big thanks to David Zilberman. He's back there. He's been my mentor through this whole time, and always great friend and always supportive. Another mentor of all. He works at Rutgers, and thank you. Yeah, it's been fun. Quick questions. I know everyone wants to break. Yeah. Yeah.
Please no ARB.
Sorry, what?
They're called, and they gotta get these transportation sector done.
Who did I tell what?
To the Air Resources Board. They have a target 2020. They gotta reduce emissions of transportation
Yeah.
sector. Go with natural gas and
I think okay. So it's
give them
important.
all.
It's important to distinguish. I think for coal, there's no doubt. There's pretty much a consensus that natural gas is going to be cleaner, unless like leakages are found to be really, really high, higher than 15%. For transportation, I'm not sure. I think infrastructure, it'd be a really risky investment to go build all this infrastructure and not know these leakage levels, and then at the end of the day, you're emitting more than you would oil. I think it's more important to incentivize electric cars. Indirectly, natural gas can make that cleaner because if you substitute natural gas for coal, the electricity comes from a cleaner source, and that's better for the transportation sector too. So that's probably what I'd say. I'd say hold off on natural gas for the transportation sector. Absolutely, yeah.
Why do you think there's such a range in predicted leakage rates? Like, why haven't people been able to come up with a number?
It's a really good question. I think a lot of it has to do with heterogeneity of like drill sites, and I think apparently a lot of leakage happens on like very sort of like it's event based. It's not just like a constant thing that's happening. So it's a matter of being able to reduce the number of these events that sort of like leak a ton of methane into the atmosphere. And I think that comes with better monitoring, better enforcement. The minute you introduce fines for leakage, I think you automatically incentivize sort of reducing these events that are happening. And so far, I mean, Colorado just implemented a pricing scheme for methane, which is a really good step forward. But even the IEA and the White House have said that you can reduce sort of climate change I think methane emissions account for about 18% of sort of climate change. And it's probably the easiest thing to reduce right now because you don't really have to reduce energy demand. All you have to do is have better technology to control them, these events. Okay.
That concludes our first session. We have some coffee, bagels, and some fresh fruit available right across the hall here.
Oh,
Wow, we'll be back at 4:00.